What's up, everybody? In this video, we're going to cover USACO's 2020 December contest at the silver level. Problem number 2, rectangular pasture. Farmer John's largest pasture can be regarded as a large 2D grid of square cells. Picture a huge chessboard. Currently, there are N cows occupying some of these cells, where N is between 1 and 2,500. So we have a chessboard worth of cells, and there's cows in different locations. Farmer John wants to build a fence that will enclose a rectangular region of cells. So no curves, it's got to be a rectangle. The rectangle must be oriented so that its sides are parallel with the X and Y axes. Okay, so no diagonal fences. And it could be as small as a single cell. Okay, so we can have a tiny one. Please help him count the number of distinct subsets of cows that he can enclose in such a region. Okay, so for example, I could get these 2 cows, I could get these 2 cows, I could get these 2 cows, I could get all of the cows. There's not any weird situations where in this particular setup where there's certain cows that I can't, like certain combinations I can't get. Let me see if I can think of an example where there'd be a combination I can't get. Okay, so let's say like I have cows 1, 2, 3, and 4. Then, for example, I can't have the set 1, 3, 4 because any fence that's going to have cow 1 and cow 3 is going to have cows 2 and 4. There's not a way I can build around that and leave cow 2 out. So I would have 1, 2, 3, 4 would be a valid set, but 1, 3, 4 in this particular example would not be a valid set because I can't get 1 and 3 without also getting 2. Also, 1, 3 would not be a valid set because it would be 1, 2, 3, and I wouldn't be able to avoid the 2. So that's what we're doing is we're looking for valid subsets. Note that the empty subset, this is important, note that the empty subset should be counted as one of these. So basically when you get to the end, if you haven't allowed for an empty subset, you just add 1 to your answer and that'll offset for the empty subset. What they're saying there is the subset of having a fence with no cow in it is a valid solution, but it doesn't count in every location. So you can't count every location as a valid solution. It's just valid sets. So an empty location in one spot and an empty location in another spot should be considered equivalent, but we can't leave the empty set out. Input format comes from terminal standard input, so just typed into the console. The first line contains a single integer n. N was the number of cows. Each of the next n lines, each of the next n lines contains 2 space-separated integers, indicating the x, y coordinates of a cow's cell. Okay, so this is another thing to watch out for. They're giving it to you in terms of x and y. You may want to convert it to row and column. But just something to kind of be aware of, because if you do X, Y as your square brackets, usually we do row major. And if you were to try and print it out, if you print this out with a for loop with this being I and this being J, then you're going to invert and you're going to end up printing, as you try to print X with Y incrementing, you're going to print it kind of rotated on its side. And then this would be your X axis going in that direction. So just to be aware of while you're debugging, you may want to put X in the second location, or just rotate the whole thing, or you can actually just pretend these are row and column numbers instead of X and Y and completely forget about the fact they said X, Y, and it'll still come out the exact same way. But just be careful about that if you're trying to interchange between the 2. Okay, each of the next n lines contain 2 space-separated integers indicating the X, Y coordinates of a cow's cell. All the X coordinates are distinct from each other, and all the Y coordinates are distinct from each other. This is really important as well. What that says is that there will not be any 2 cows that are horizontally equal to each other or vertically equal to each other. So my example before where I had 1, 2, 3 would not be possible. They would have to be diagonal to each other, 1, 2, 3. So if you had that, then still we wouldn't be able to have the set 1, 2, 3, but they wouldn't be exactly lateral. In this case though, we could have cows at 1, 2, 3. We can have the set with 1, 2, 3, but we can't have the set with 1 and 3 because 2 is right in the middle. So the same issue is going to come up. It's just confirming that they can't be horizontal or vertical to each other. They all have to have different X values and they all have to have different Y values. All X and Y values must lie in the range of 0 to 10 to the 9th. Okay. There's a couple optimizations we're going to need, and this actually is indicating another one of them. Let me read the output format first. The output format is the number of subsets of cows that Farmer John can fence off. It can be shown this quantity fits within a single 64-bit signed integer, aka a long. Okay, so that's another thing is we're going to have to be using longs. So the number of subsets is going to be quite high. So we'll go back to this first optimization though, because this is really important. We only have 2,500 cows. But it says the cows' X and Y values lie in the range of 0 and 10 to the 9th. me scroll down a little bit. So what that means is that we could have 2,500 cows spread over a billion, a distance of a billion. But the distance doesn't actually matter. We're only counting subsets. So whether or not we've got cow one, like a cow here, and then a cow very far away, or whether or not this cow is close, that doesn't actually really make a difference. So what's going to happen here is we're going to first want to compress our coordinates. Say, for example, I have a cow at 0, 0, and another cow at 1,000, 1,000, 1,000. If these are the only two cows, the fact that this is 1,000, 1,000 is irrelevant. It's exactly the same as if it was 1, 1. That would not change the problem. The empty space doesn't actually do anything to change the problem. All this empty space in here is not accomplishing anything. So the first thing you're probably going to want to do is compress your coordinates. Let's use the sample input case here to show why that would be the case. I'm going to use X and Y rather than rows and columns, just because that's kind of how the problem's set up. So this is my X axis. This is my Y axis. So I've got 0, 2, 0, 2, there's a cow here. I've got 1, 0, let's do 1, 0, 1, 0. I've got 2, 3, 2, 3, there's a cow there. Then I've got 3, 5, and then 5, and then there's a cow there. Okay. There's 4, 3, 2, 1. So, oops, 2, 3. Yep. Okay. Okay. So notice, for example, that there is no cow with a Y value of 4. So what that means is if I wanted to eliminate that Y value of 4, I could take this cow that has a value, the 3, 5 cow. I could lower that down to 3, 4. And that doesn't actually change the problem. Notice also I don't have a cow at the Y coordinate of 1. So I could get rid of the Y coordinate of 1 as well. I could move this cow, so I'm gonna erase that. Yep, I can move that cow down to 1. I can move this cow down to 2. I can move this cow down to 3. Let me clear those guys off. Okay, so now this is the exact same problem, but what's happened now is I don't go up to 5 anymore. I only go up to 3. So I have an X value of 0, 1, 2, and 3, and I have Y values of 0, 1, 2, and 3. Every X value has a cow and every Y value has a cow. And I just did that by eliminating space. This is especially important if you're going to have, like, for example, if I have a cow at like 100,000 and 100,000, then I might as well bring that down to 4, 4. The reason why I'm going to want to do this is because we're going to have to actually use dynamic programming. This is going to be a 2D prefix sum situation. If you're not familiar with 2D prefix sums, you probably are going to want to take a break, maybe pause this video. I have a video on 2D prefix sums that reviews it, but you're going to want to understand that prior to moving on. I'm not going to go into it in too much detail here, but essentially what's going to happen is we're going to consider, as we iterate through this, basically every pair of cows. And for every pair of cows, for example, this cow right here, oops, this cow right here, and then this cow right here, we're going to consider that pair of cows. And then we're going to look at how many cows are to the left of it, how many cows are to the right of it, and we're going to basically just multiply. So what's going to happen is if I have a setup where I've got 2 cows over here and 1 cow over here, because this is 2 cows including that one and 1 over that one, then each of these cows is a potential starting point for a rectangle. What's going to happen is, since all my Y coordinates and all my X coordinates are distinct, every single pair of cows is going to define a distinct pair of Y coordinates. So this pair of cows defines the distinct coordinates of 0 and 2. The pair of cows, let's see, this pair of cows here, this one and this one, define a distinct set of Y coordinates. So for every possible set of Y coordinates, I want to know how many cows, potentially, how many rectangles there are for that set of Y coordinates. In the case of these 2 cows, there's only 1. Because if I look at this here and this here, the number of cows to the left of the left cow is 0, and the number of cows to the right of the right cow is 0. But I'm guaranteed to have a set. As long as I've got 2 cows selected here for a pair of Y coordinates, I'm guaranteed to have at least 1 rectangle. But if I had a cow over here, then that would be a second rectangle. The cow on the right still forms the right side, but now the cow on the left, there's a different cow on the left, and that would be a different set. If I were to have multiple cows on each side, for example, let's say like I have 3 cows over here and 1 extra cow over here. Then again, using this cow and this cow, which we are guaranteed to have as distinct, and setting up that parameter, then on this side, on the left side, I've got 3 cows. On the right side, I've got 2 cows. So the number of boxes I'm going to have there is going to be starting from this cow and ending on the first one, starting from this cow and ending on the second one. This cow is a left side, has 2 potential right sides, one with the first cow, one with the second cow. Then moving on to the next cow, excuse me. The second cow here has 2 potential stopping points, the first one and the last one, because there's a left side with a right side here and a left side with a right side here. And then moving on to the third and final cow here, again, same 2 stopping points, because I could have a left side here with a right side here, or a left side here with a right side here. And that would be all of the potential rectangles using this one as a top and this one as a bottom. So just to kind of explain shorthand how that's going to work, once we have our cows, let me clean this up a little bit. Once we have our cows picked for the pair, the way that we know how many there are is basically including this cow, how many cows are to the left of it. And then for the right side, including this cow, how many cows are to the right of it. I'm going to put back what I had before with the 3 cows and then the 2 cows. So if I've got a total of 3 cows on the left and 2 cows on the right, then I've got 3 potential stopping points with 2 potential starting points. 3 times 2 equals 6. That's how many cows I would have to add to my total, because for that particular pair of y coordinates, that's the number of unique rectangles that's going to be produced. So the way the problem setup is going to work, let me kind of clean this up again. The way the problem setup, and remember, every single pair of cows defines a distinct x and a distinct y point. So because every single pair of cows is every single pair of cows is 2 distinct y points. So we'll have to look at every single possible combination of cows, and that's going to be n squared. But that's okay, because 2,500, we have 2,500 cows. So 2,500 squared is, what is that? Let me just real quick plug that in. 2,500 squared. 6 million. So 6 times 10 to the 6th. That's tiny. That's plenty fast enough. So we've got an n squared number of potential pairs of cows. But what we want to do is we want to know then, head back over here. We want to know then how many cows are for that section on the left and how many cows are on the right. So if I have 6.25 million. If I have 6, let's just do 10 to the 6th. I have about 10 to the 6th pairs of cows. So if I have 10 to the 6th pairs of cows, I cannot afford to run through all these cows and add them up, because that's going to be another n, and that's going to put me at 10 to the end of the 3rd if I have to count up cows, which would be, what is that? Way too big. 3, 6, 9, 10, might be 10 or 11. Yeah, that looks like it's 10 to the 11th power. It's too big. So what we need to do is we need to figure out a way to optimize the process of, once we've picked our top and bottom pair of cows, which again, we can do that in n squared time, we need a constant time way to figure out how many cows are to the left and a constant time way to figure out how many cows are to the right. And that's what 2D prefix sums is going to do. And again, I'm not going to go into that in too much detail here, but I'll show you how to set the problem up. Essentially what a 2D prefix sum is given a row and a column. For example, if I know that my dimensions are here and here, then what the 2D prefix sum is going to do is, I know my x value, I know my y value, and in order to figure out this area, it's the value here in the grid minus here, plus here. And that's going to tell me what's in that area. And if you're familiar with 2D prefix sums, you already know why that is. You'll do that same thing on the right side and figure out how many cows are in this territory here, again, by doing this minus that, plus that. And then that's going to tell you how many cows are there. You'll multiply the two. And then from there, it's just a matter of iterating through every single possible y value. And that's very easy to do also if you compress your y values, because then you're not going to have any empty space. So let's kind of just briefly run through how that's going to work with these cows. So I've got cows at 0, 2. I'm going to write them, since they're all one digit, I'm going to do 0, 2, comma, 1, 0, comma, 2, 3, comma, 3, 5. First thing I want to do is I'm going to sort these cows by their X position, and I'm going to run through and assign them incrementing X values, which I think is already done because these are already sorted by X, 0, 1, 2, and 3. I don't have any skipped values. If, for example, my numbers were 0, 2, comma, 1, 0, comma, 3, 7, comma, and then like 8, 9, then what I would want to do is this is 0, that's fine. This is 1, that's fine. This 3 should just be lowered to a 2. And this 8 should just be lowered to a 3. Because again, we don't need empty space. So this is just how we're going to eliminate empty space. You sort by your X value, you break all your X values down so they're just increasing 0, 1, 2, 3. So that's already done with the initial data set, but if that 3 happened to be larger, I would lower it to a 3. Having now done that, I'm now going to sort by Y. So it's going to give me 1, 0 first, 0, 2 is going to be second, 2, 3, oops, 2, 3 is going to be next, and 3, 5. I'm going to repeat the process on the Y value. This must be a 0, this must be a 1, this must be a 2, this must be a 3. Okay, so what I have here is the exact same values as the starting, but my cows, two things that's happened to my cows. First is my cows are now sorted by their Y values, 0, 1, 2, 3. Second is there's no missing Y values. So if I were to rewrite these, considering my X line, X having a value of 0, 1, 2, 3, then I've got, let me see, 1, 0, give myself some more room, 0, 1, comma, 2, 2, comma, 3, 3. All right. Clear this out. Okay, so what I've got here is I've got my X line, every X value is unique, and I've got my cows sorted by their Y. So the first cow is at X1, and then Y0. Let me actually put that up on the line just to have it there. First cow is here. Second cow is X0, Y1. So I'm gonna draw this upside down with Y going down, so it kind of follows rows a little bit more. I've got a cow at 2, 2, and I've got a cow at 3, 3. So what I'm gonna do then is I'm gonna make a for loop for I from 0 up to N, and then for J for 0 up to N. And in this case, actually no, sorry, this should start at I, for J from I up to N. One thing to point out is it is possible to have a single set cow. So we might as well just wrap these in. If you have one single cow, since you're guaranteed to have X and Y be unique, then if you make a calculation here, you're just gonna have one cow on the left and one cow on the right, and that's just gonna count as one. Just making sure that you include it. The math should be fine on that. Otherwise, what you can do is you can have J start at I plus 1 and then just add 1 for every single cow. You can add N at the end. However you want to do it, it doesn't really matter. So, again, this either should be I plus 1, and then you'll know that every single cow can be an empty set, so you'll just add them in at the very end. Or you can start it at I and feed it into your formula, and it probably is going to work either way. So, I plus 1 and then just add N at the end, or I, and then just make sure your formula is solid. But basically what we're going to do is then for I and J, that's going to come up with every single possible pair of cows. So like when I is here, J will be down here. That's a pair of cows, X and Y, top and bottom cow. J will move its way down here. Then this will be a pair of cows. And that forms that spot right there. J moves down to here. And then this becomes a pair of cows here to here. And then again, each time you're looking at the left side and the right side to count how many sets there are. In this case, for example, with the first and the bottom cow, we've got 2 potential sets. One of the sets is this cow, this cow, this cow. One of the sets is all 4 cows. And the way we would calculate that again is by looking at the number of cows to the left, which is 1 plus 1. That's 2 potential starting points. And then this cow is by itself on the right, which is 1 potential ending point, and 2 times 1 is 2 potential rectangles for that particular range. Okay, so once we have this set up, we need to convert this into a 2D prefix sum. So I've got, let me see, clean up this, I'll put a little bit. So basically what we're going to do then is we're going to draw our grid. I'm actually going to just completely clear this out. We're going to draw out our grid and do our 2D prefix sum. The way that's going to look is anywhere that there's a cow, we just put a number 1. So we'll start with our 4x4 grid. 1, 2, 3, 1, 2, 3. So I've got a cow at, I'm going to switch this to rows and columns just to make life easy. So I've got a cow at 1, 0. I've got a cow at 0, 1. Actually, this looks like it's symmetrical, so it doesn't matter anyway. I've got a cow here and a cow here. We fill out our 2D prefix sum table, which again, I'm assuming that you have familiarity with that. If not, take a break and go look at how 2D prefix sums work, because I have a video that goes into this in extensive detail. 0, 0, 0, 0, 0, 0, 0, 0, 0. I had a 1 here, a 1 here, a 1 here, and a 1 here. So, okay, so 1, and then this is 1 and 1. From here, this is going to be 2. This will be 2, 3. This will still be 2. This will still be 2. This would be still 1. This is going to be 2. I think I messed that up. Let me look at that again. Trying to do this too fast. Okay. If you're not familiar with 2D prefix sums, just very briefly, the way this works is when we're filling out our chart, we're adding the number above, we're adding the number to the left, and we're subtracting the number diagonal. Every one of these boxes represents the total of the number of cows that are, in the rectangle up and to the left of it. So if you look at, just kind of looking at this, I've got 1 here because there's 1 cow up into the left. I've got 1 here because there's 1 cow up into the left. If I were to consider this box, that only contains 1 cow. If I consider this box, that only contains 1 cow. From here, there should be 2. And the reason why is because the number of cows that are up and to the left of that location is 2 total cows. So that's what we're trying to do, is we're filling out our 2D prefix sum just based on counting up how many cows are above and to the left. So 1 cow here, 1 cow here. This is 1. This will be 2 all the way across. 2, 2, and 2. This will be 1 cow, 2 cows. This is where it hits 3. And then still 3. This will be 1, 2, 3, and 4. Okay. So, and again, what these numbers are, each of these numbers represents the number of cows up and to the left. So this is a 3 right here, because if you correspond it to this box, that corresponds to this box. The total number of cows up and to the left are 3. This down here is a 3, because if you consider this box, total number of cows above and to the left is still 3. Same thing with this one over here. That's a 3 because there's 3 cows in this territory. And this one is a 4 because up and left from that bottom corner, there's a total of 4 cows. Okay, so once you have your 2D prefix sum set up, basically then you're having I and J run through this. For every single pair of cows, let's actually use the left side because then you can see where the cows are. I and J are going to run through. For every single pair of cows, you use your prefix sum table to figure out how many are to the left and how many are to the right. So let's look at J equals 2, because that's actually one of the, for this sample case, it's really the only interesting one. So if I have a J of 0, an I of 0 and a J of 2, then that's checking this cow right here and then this cow right here. And I'm going to have this 1 extra cow on the left. So the way this prefix sum table works then is I'm looking at from here, that's 1 of the cows, and from here, that's 1 of the cows. So I can use my 2D prefix sum table. If I take the bottom value here, 2, and then subtract 1, and then subtract 0, and then add 0, that'll tell me that there is 1 cow to the left. Actually, it should be 2, 0. I think I gotta go to the top. Yeah, I gotta go to the top. I gotta go further. From 2 to 0 to 0, and then adding in the 0 will tell me that to the left of this position in this territory right here, there is 1 cow. And then I'll just, well, there's 2 cows, I guess. We probably should do it from here. You do it either way, actually, I think. You can either do it including the cow or do it excluding the cow and add 1 to the result. But basically, you're going to use your 2D prefix sum table to calculate what is in this territory right here. Like that. And again, that's this value, yeah. So if we want to do left side, it would be this value minus the value on the top, minus the value on the top, plus the value on the corner. That'll give us 1 cow. Add 1 to it because we know that the cow has to be included. And then we'll do the same thing on the right side. We have, let me clean this up. This cow down here. So we want to calculate the right side of that cow using this cow as the top, I as the top. We want to figure out this space right here. How many cows are there? And that's going to be in our 2D prefix sum table. That's this guy right here in this area. So to figure that out, we do 3 minus 1 minus 3 plus 1, which is just going to be 0. That tells us there's 0 cows over here. But then we have to add the 1 here. So that'll be 1 on the right side, 2 on the left side. you multiply those together, that's 2 times 1, and that tells us that for this range of I to j, there are 2 potential rectangles. And the way we figured that out is just figuring out how many cows are on the left, how many cows are on the right. In this example, there were 0 cows on the right, but we have to add 1 for the bottom cow. And there was 1 cow on the left, we had 1 for the side cow, so it ends up being 2 times 1, and that gets added to your total. And then you just run j through and try every possible combination of I and j. And again, if you're familiar with prefix sums, then actually this problem is pretty straightforward, because basically what you're going to do is you first compress your coordinates so you don't have any empty space. Every single I and every single j then, as you loop vertically, is going to correspond to a cow. That's a valid cow location. And then what you're doing is you'll want to use your original cow set. And remember the original cow set, if you think back, the last thing we did was sort by Y when we did the compression. So when I'm referring to I and j, in order to find the X value, this can be I and this can be j. So if I have my cows still stored, I can immediately check to see the X value of I and the X value of j. I don't need to actually search my table for it. So as I and j are looping through these pairs of cows, considering every pair of cow, they're already sorted by the Y values, 0, 1, 2, and 3. So that I can just use that straight on the chart. For every single pair of cows then, whatever that pair is, I and j, I get the X value of 1 and the X value of 2, figure out which cow's on the left, figure out which cow's on the right. I know which cow's on the bottom because it's going to be j because they're sorted, and which cow's on the top. Once I have that territory, and this is all scribbles at this point, it's kind of hard to read. Once I have that territory marked out, I've got my I, which is my top. I've got my j, which is my bottom. Between those 2 X positions, they're not necessarily in order because it's not sorted by X anymore. So we figure out which of those 2 is the left side, which of those 2 is the right side. And then that sets up our territory here. Then all I need to do is use the prefix sum to figure out, given whatever the left side is, which could be I or could be j, with j as a bottom and I as a top, from there all the way to the left, all the way to the edge, basically, how many cows are there? And then repeating the process, whichever cow is on the right, I have my top and my bottom, and I go from whatever the very far right side is, which is at most n, because we have n cows, so at most that's going to be n, but whatever that far edge is, use the prefix sum to calculate how many cows are in this territory, and again add 1 to it for the cow that's forming the border. Once you figure out how many cows are on the left and how many cows are on the right, you multiply them together and add that to your total, and then just remember to add +1 at the very end for your empty set. That's an easy thing to forget. I actually missed that myself because I didn't read this the first time I did the problem. So that's just something to watch out for, and more reason to always read all of the instructions carefully. If you missed the empty set should be counted as one of these, you would miss every single problem. Unless did they say that there's possible to have n equals 0? I don't think there's an n equals 0. Yeah, so you pretty much would miss every single test case if you didn't add in that empty set, because even with 1 cow, there's going to be 2 sets. So always read all the problems, instructions carefully. So yeah, so then that's it. Just as a real quick recap, take these guys, compress the coordinates so that we don't have empty space, set up a 2D prefix sum table. And if you're not familiar with that, review my video on that. For every single, once you've sorted by X and then sorted by Y, leave it sorted by Y. As I and J go through, it's already sorted by Y, so you can use your original cow set to figure out the X values. Given the leftmost X and the rightmost X, whichever they happen to be, and the I, which will be the top, and the J, which is the bottom, set up your territory, use the 2D prefix sum to figure out how many cows are on the left and the right, multiply them together, add that to your total, and then just remember to do +1 for the empty set at the bottom. And that's the problem. Good luck coding it, and I will talk to you on the next one.